Okay, in this video, we'll do another example of a related rates problem. So let's say that 2000 r squared equals n cubed relates the number of employees for a business with the revenue. So this will be, n is in terms of thousands of employees, and r is in terms of billions of revenue, billions of dollars in revenue. So let's say at some point in time, there are 180,000 employees, and there is 54 billion US dollars in revenue. Okay, for the company, I suppose for that year, right? Now let's assume that the revenue is increasing at, let's say, a rate of 7 billion per year. Let's say 7 billion per year, US dollars per year. Okay, and the question is, at what rate is the number of employees changing? Well, we need to interpret these numbers given that these variables are in terms of multiples of employees and multiples of dollars, not just, n equals 5 is not 5 employees, it's 5,000. So here, where I have 180,000 employees, if n is in thousands, that means that n is 180 in that case. If I don't handle these numbers correctly, I won't get the right result. The 54 billion, well, since r is in terms of billions of dollars, that means that r is 54. Okay. Now this last one is maybe the harder one. What is it that is 7 billion? Well, this is revenue increasing $7 billion per year, so something is 7, right? If you think about it, maybe pause the video and think about it. This is the rate of change in the revenue as a function of time. So this is dr dt. dr, make it a little bit neater, dr dt equals 7, okay? So now if I want to know the rate of change in the number of employees, from year to year, how is that number going to change? I can use this original equation. I can find the derivative with respect to time of this equation, plug in the numbers I'm given, and then I can find out here's the rate of change in the number of employees. So let's do that. I'll just copy the equation down here. So 2000 r squared equals n cubed. Okay, so when I apply the derivative to both sides, d dt, on both sides, then this is a lot like ones we've done already. This is not super difficult. We just have to remember that we are using the chain rule. The variable with respect to which the derivative is being taken is not the same as the variable in the equation, or variables, I should say, in the equation. So I have to use the chain rule for every derivative. I'm not just using the power rule here. So using the power rule, I'm going to have 4,000 times r to the first power, that's the power rule, times dr dt. It's the chain rule. Okay. Let me change colors real quick. Power rule, chain rule. Okay. And you're always going to be considering the chain rule. You might not always be doing the power rule. Just in this case, we are, because we have r squared and n cubed. We're using the power rule. But for this kind of problem, you're always going to be using the chain rule. Okay, so the right-hand side will be done similarly. When I apply the power rule, 3n squared, that's the derivative of the outside function, then times dn dt, it's the derivative of the inside function. Okay? And now I have an equation that relates r, dr dt, n, and dn dt. Now I have numbers for 3 of these. n, r, and dr dt, I have numbers, so I can plug those in now. If I had plugged in 180 and 54 at the beginning, I wouldn't get a result this way. I mean, I would get, what would that be? I don't know what n cubed is, but I would have some number equals some other number. The two sides would be equal, and I wouldn't really be able to do calculus with that. I have to plug in my numbers after I apply the derivative. Okay, so n is 180, r is 54. So r is 54, so 4,000 is 54. DRDT is 7. And N is 180. Okay. And DNDT, that is what we're looking for, the rate of change in the number of employees as a function of time. So now I can divide both sides by 3 times 180 squared. So I'll have 4,000, and we're probably going to use a calculator at some point, times 7 over 3. And I'm going to write the 180 squared a little bit differently. I'm going to write it as 180 times 180. Okay, that equals DNDT. You'll see why in a second, why I'm doing that. Now, we are going to use a calculator, but if I see any ways to simplify things, I can do that first. So I notice this 0 and this 0 can cancel, this 0 and this 0 can cancel. And I notice that 3 times 18 is 54. So 3 times 18 and 54 can cancel. So I've got a little bit less to type in. This 40 and this 18 can reduce. So I get, what is that, 140 over 9? I think that's right. Simplify that a little bit, and then we can throw that in a calculator and get a decimal number. So 140 divided by 9, I get 15.555 repeating. Let's round to, say, 3 places. So 15.556. Okay? Remember, this is the number of employees in thousands. So that means the conclusion we draw is 15,556 more employees. It goes up because the value is positive. More employees, say either that year or the following year. Oh, that is not how you spell employees. Either that year or the following year, depending on the way the question is phrased. Yeah, so basically we take the information we're given, we make sure to interpret these numbers, we take the scale of the problem into consideration. Employees is in thousands, revenue is in billions. That's very important. Then we apply the derivative with respect to time to both sides of the equation. Okay. Then we plug in the numbers we're given, and then we work out what the result is. And we might need to interpret, well, is this more employees or less employees? That's something we might have to figure out as well.